Okay, let's begin. All right, good morning, everyone who's here and who's online. Let's continue with chapter 3. We'll wrap up chapter 3 with a little bit of the theory, and then there are 4 examples, example problems. I was checking the calendar for the homework, and now I can't remember when it was due. Let's see. Let's bring up. So the assignments. I'm just checking the due date for the homework for chapter 3. So 10th. So it's supposed to be due tonight. I will push it back till tomorrow. Okay, since we have not yet solved the examples in class. A lot of the questions you would be able to answer based on the theory material that has already been covered. But the problems I will cover today. All right, so let's go ahead and bring up the class notebook. Homework number 13, yes. Okay, so brief recap. We are studying inductors and capacitors in this chapter. Both of these are passive components, passive linear components, similar to resistors. But unlike resistors, capacitors and inductors are energy storage devices. They can receive energy from a source, and they can store it for a period of time, after which the energy is released back into the circuit. The energy transfer back and forth from these components does not take place instantaneously. It takes a finite amount of time, and that time is dependent on the circuit conditions, the size of the components, as well as the energy that is being supplied from the source. The energy transfer portion of the analysis is something we'll study in chapter 4. Right now, we are doing a general or broad overview of these capacitors and inductors. So we covered inductors. Inductors store energy in the form of an electromagnetic field. Capacitors store it in an electrostatic or electric field. The inductor equations, primary equation is in terms of the voltage. Inductor voltage V is given by the product of L and the derivative of the current with respect to time. It is the rate of change of time. So inductance times the rate at which the current changes. That is di over dt. If the current does not change, meaning it's constant, the oncoming input current is DC, then this quantity di over dt goes to 0. That goes to 0. That means the voltage across the inductor is 0. In physical terms, if you apply a DC current to an inductor, the inductor behaves like a short circuit. Behaves like a short circuit. Okay. For an AC, it opposes any change in the current. For an AC input current, the quantity voltage or current is always changing. The value is always changing. Hence, the inductor will oppose this change. But again, that's a topic for chapter 5. And then we came to the capacitor. Capacitor. We looked at the physical construction of the, actually, no, we haven't yet looked at the physical construction. I think I explained the primary equation, which was capacitor current I is the product of the capacitance C times dV over dt, the rate at which the voltage changes. Okay, the voltage that is applied to the capacitor, the rate at which it changes, which is dV over dt. So if you apply a DC voltage to a capacitor, if you apply a DC voltage to a capacitor, then dV over dt is 0. Hence, a capacitor acts like an open circuit, meaning once the capacitor reaches full charge, it receives all of the energy that it can store. From that point on, the capacitor does not charge anymore, does not receive any further charge, so it behaves like an open circuit. And again, this is for an applied DC voltage. On the right here, I was showing how we can use different different notations depending on the author, the publisher, depending on sometimes it depends on the circuit. We can have a subscript, we cannot have a subscript. In both cases, it means exactly the same thing. We could also describe it as a function of time. So voltage or current for an inductor or a capacitor can be described as simply by V or I, or V of t and I of t as a function of time. They both mean one and the same. Sometimes we have an additional subscript to indicate the component itself. So if it's VL or VC, it indicates inductor voltage, capacitor voltage. If there's an additional function of t, it still means the exact same thing. All we are saying is that the quantity voltage or the quantity current is a function of time. Any questions before we continue? Okay. All right, so then let's go here. So in these illustrations, in these diagrams, I was showing how a capacitor is charged. Now, once a capacitor is charged, you could possibly remove it from the circuit. And once we remove it from the circuit, the capacitor would hold its charge indefinitely. Now, this is, of course, for an ideal capacitor. Real-life capacitors do not behave this way. Real-life capacitors will actually discharge through the insulator and through the air. Okay, so a real-life capacitor is modeled as an ideal capacitor which has a resistor in parallel. This resistance would be modeling the resistance of the insulating material. The insulating material, of course, can be made out of any dielectric material, any insulating material. Typically, it's very, very thin layer on the order of like microns. For an ideal capacitor, this R is infinite. Real life capacitor, it is very high, but the capacitor cannot hold its charge indefinitely. It will slowly discharge. Okay, at some point it will lose all of its charge. And at the same time, I'd like to talk about a real-life inductor. I think this is something that was not mentioned earlier. So here, stated that once the inductor reaches full charge, it behaves like a short circuit. Well, at that point, inductor, let's see, let me do it here. So a real life inductor is made out of a coil of wire. A coil of wire inherently has some resistance. Doesn't matter how good of a conductor you use to make that inductor, a real life inductor will always have some resistance. So if you take a piece of wire, you measure the inductance. Once you wind it up in a coil, you measure the inductance between the two ends. You will measure some inductance. If you measure the resistance, it will give you some value for that resistance. Okay. And that resistance is inherently part of that wire. So we cannot separate it out. And so we cannot separate it out. We model it as a resistor that is in series with the ideal inductor. Okay. So let's say this is the inductor you're looking at. Ideal inductor. This would be a real life inductor, which has a value of L, and this resistance will have a value of RL. Sometimes this RL, inductor resistance, is also noted as the DC resistance of the inductor. Okay, it is inherently part of the inductor itself. We cannot separate it out. So obviously, because it's in series, it interferes with circuit operation. So we describe the inductor quality based on the resistance value. Obviously, we want the value of RL to be as low as possible so it doesn't interfere with the circuit operation. And the quality of that inductor is described by the value of that RL. Ideal inductors, RL is equal to 0. Real life inductors, high quality inductors, the resistance is less than 4 or 5 ohms. All right, let's take a pause. Let me know if you have any questions at this point. Yes. We can calculate and we can measure it. So there are LCR meters, the orange one that you see on the bench here, on the cart, and there's a function where it measures the inductance and also measures the resistance at the same time, performs a calculation, and it gives you the value of the Q. And the reason I was gonna say I'm not stating it right now, but I can state it. It's Q is given by the ratio of XL to RL. XL is reactance, which is what we'll study in chapter 5. That was the reason I was not going to mention it. But that equation has, so QL, quality of the inductor, is XL over RL. The XL is not something we'll see until chapter 5, but RL is in the denominator. That's the key point. RL is in the denominator. If RL is 0, quality is infinite. Right? At least that would make sense. Even without knowing what XL is or what it does, RL is in the denominator. So if RL is equal to 0, quality is infinite. So the higher the value of the resistance, the lower the quality. All right, any other questions? Okay, let's go back to our capacitor discussion. Okay, so if you have a fully charged capacitor, we can remove it from the circuit. Ideal capacitor will hold the energy infinite, for an infinite period of time. Real life capacitor will discharge slowly but surely through the insulator and the air. If you take a fully charged capacitor, even in real life, and you take it out and you short the two leads, all of the energy in the capacitor is released all at once. So if you short it out, shorting a capacitor means you connect a resistor with a value of R equal to 0 ohms between its two leads. And in general, if you have an energy source or trap energy in any component, if you connect the two ends or two terminals together, all of that energy is released all at once. And so with a capacitor, you will see a small spark. Well, depending on the size of the capacitor and the stored energy, because that energy is being released all at once. Now, if it was a battery, then it's completely different. Just going on a little bit of a tangent. A few years ago, Samsung released the Galaxy Note 7 smartphone. Did you all hear about it in the news? The phones were exploding. Remember, that's when worldwide everyone started banning lithium-ion batteries or rechargeable batteries in flying in the checked-in cargo. Well, what they did was, at the time, Samsung engineers, in the pursuit of making the phones thinner and thinner and thinner, they decided to make the compartments between the battery that was inside the smartphone, the compartment walls inside the battery, very, very thin. And so a mobile phone or a laptop battery is made up of individual cells. And so there are divisional walls between each cell. And of course, I don't know the exact design of the battery that they had inside it, but what happened was, because of the thin walls, there was a short circuit between the cells that were next to each other. And so there was a continuous pathway from the positive end of the battery to the negative end of the battery. And because it was 0 ohms, or very, 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 very low resistance, that battery energy was being released all at once. So in real terms, I is V over R. If this R is 0, I goes to infinity, right? If R is 0, I is infinite. If I is infinite, then your power and energy is also infinite. Make sense? So all of that energy stored in the battery is being released all at once. Now, if it is a capacitor, the capacitor only has so much amount of energy stored. So you short the two terminals of a capacitor, that energy is released, and that's it. Nothing else. You'll have a small spark, and you won't have anything else further, because the capacitor is now depleted. All of the energy is gone. But if it is a battery, the batteries, of course, also have finite amount of energy, but that energy is a whole lot more than what the capacitor can supply, right? And so the battery is now releasing energy constantly. And once it is releasing energy constantly, excuse me, once it is releasing energy constantly, what happens? Energy transfer, electrical energy gets converted to thermal energy, dissipated as heat. That battery starts getting hotter and hotter and hotter. And at a certain point in time, the energy gets so much, battery swells up, there is no place for the energy to go, and the phone explodes. And that is what happens when you short circuit two terminals of a battery. And so that's what happened with the Samsung Note 7. All right, makes sense? And that's also what happens when there's a short circuit in a power outlets. R goes to 0, the two ends or the two terminals are now connected together. All of the energy, this infinite amount of energy that's coming for a long period of time, is being released all at once. If you don't stop it, end up with fire. And so we install fuses, we install circuit breakers. So it really goes beyond a certain limit. A fuse has a very thin point of wire that just blows out. It literally just blows out, causes a disconnection in the circuit. With a modern circuits, we have circuit breakers all around. Okay, let's see. So capacitance is basically, the word capacitance comes from the word capacity. It's capacity of that component to store charge, to store energy. And it's given by this primary equation. Capacitance C is Q over V, where Q is the standard charge. And V is the applied voltage. Okay, So again, capacitance is the amount of charge that the capacitor can store for every unit of voltage applied. From there, we get the equation Q is equal to CV. And from Q is equal to CV is where we obtain the primary capacitor equation. Because if you take the derivative of Q is equal to CV, you obtain dQ over dt. dQ over dt is the rate of flow of charge. And the rate of flow of charge is nothing but current I. Okay, rate of flow of charge. dQ over dt. And that's where we get the primary capacitor equation. I is C dV over dt. That's where we get it from. And capacitor is a passive element like resistors and inductors. And so it follows the passive reference configuration or the passive sign convention. Point of entry of the current is always plus, point of exit is minus. And conversely, if you have a voltage plus, then current is going from high to low, meaning flowing from plus to minus. All right, let's take a pause. Let me know if you have any questions. Any questions at all? Yes. So the question being asked is, how much energy can the capacitor store safely? Like with any component, we can oversupply energy. And so if that happens, it will absolutely, as you stated, that it will blow out. So I have a battery charger right now that had a blown capacitor just because the capacitor was like cheap. And so I think one evening I was charging like, 4 cells in there, and probably the energy being, passing through that capacitor was too much, and I heard something pop. And so that's what would happen. Same thing with the resistor. If the current going through or flowing through a resistor, the voltage applied across a resistor causes too much current to flow through, and the resistor is not able to dissipate all of that energy, it'll blow out. And that's what would happen. Yeah. Yes. For the power, so that would depend. So the question being asked is there a formula and equation? The answer would be there's a standard power equation. And when, of course, that depends on the physical construction of the resistor or the capacitor or the inductor, for that matter, right? For a conductor, and again, going on a little bit of tangent, if this is the cross section of a wire, let's say this is the cross section of a wire. This is the diameter D. A cross section would give you an area. The resistance of this wire is rho L over A. So depending on how long it is, how long the length is, you have the resistance of that wire. Now, the reason I'm talking about the resistance is because depending on the resistance or the size or physical size of that conductor will determine how much current it can carry. So a very thin wire can carry a limited amount of current. And there are more physical equations, that go into that. but that's where it comes from. And so if the current increases, that thin wire cannot dissipate that heat, quickly enough. It'll just get so hot that will blow out. And then that heat carrying capacity is dependent on the material of the wire as well as the amount of current that's flowing through. We use this every day in real life. If you have ever used a clothes iron or a water heater, clothes iron has a coil inside it, multiple coils inside it. And those coils, when electric current passes through, it opposes the flow of that current. And because it opposes the flow of current, it gets hot. Now, when it gets hot, if it was made out of very thin wire, it will just blow out. But it is designed to actually just dissipate the heat as much as it can. It gets hot, we can use it for ironing clothes. There's handheld water heaters that you can immerse in water and make it water. And then, of course, cooking stoves. You have those electric coil cooking ranges. If you have access to one, you just turn it all the way to high. Within a few seconds, it's going to get so hot, it'll turn bright orange. Anyone ever done that, seen that, right? And that's exactly the same principle. That coil has resistance. When you turn it on, electric current is passing through it. Depending on how high or low you turn it up, you're controlling the amount of current that's actually going through that coil. And so that current is being opposed, coil gets hot, but that coil is very thick, made out of very high resistivity material, and so it can dissipate the heat enough so that it doesn't blow out. Now, if you had access to like a really high voltage or high current source, and you connect the same coil to the high voltage and high current, we would be able to blow that out too. Hopefully, none of you listening here have that. Okay, any other questions from anyone? Okay, all right, so just a few examples based on this equation. I'll go through these quickly, simple examples. There's nothing, it's just to explain the concept of the capacitance, right? So if you have a standard capacitance, let's say of 3 coulombs per volt, you can apply 2 volts to it. If you apply 2 volts to it, it can store 6 coulombs of charge. Okay, 6 coulombs of charge. So if you wish to store 6 coulombs of charge for an applied voltage of 2 volts, you need at least capacity of 3 coulombs per volt. Unit for capacitance is named after Michael Faraday. And farad. 1 farad. If you wish to store a higher amount of charge for the same amount of applied voltage, in example B, we have 12 coulombs of charge for the same 2 volts. So now your capacitor has to be much bigger. It requires 6 farads. And the third one, you can see 12 coulombs, but now you increase the amount of voltage it can handle, and the capacitance required is only 1.5 farads. Okay, so if you increase the amount of voltage, you can reduce the amount of capacitance that is required. And right now, without knowing the physical dimensions of the capacitor, physical construction, these numbers don't make sense. So in the next slide, we'll talk about the physical construction of a capacitor. Let's take a pause before we get to the next slide. So yes, that's absolutely correct. So the question being asked is about the size of a capacitor and whether 1 farad is a big capacitance. And the answer is yes, it is absolutely a huge amount of capacitance. Real life capacitors are actually bigger than resistors, but the capacitance is measured in microfarads. Okay, So 1 farad is a huge amount of capacitance. It would be like a big cylinder, bigger than a battery, bigger than a D-sized battery, that could sit on your circuit board. If you look at that circuit right there, that's a huge capacitor. Well, actually, multiple huge capacitors sitting on them. And these are 1,800 microfarads, 350 volts. Yeah, the big round cylinders. You can pass that around, that's fine. Typical ones I've seen, the maximum ones in real life I've seen was like an AC adapter, like the adapters that we use in laptops. When we use transformers in those adapters, it would be about 1,000 microfarads or 10,000 microfarads. And so 10,000 microfarads would be about, what, 10 millifarads. You know, still far less. So 0.01 farads, still far less. This one has about, what, 1,800 microfarads. So it's 1.8 millifarads. But the huge size is because of its voltage handling capacity. It's 350 volts because the physical components inside the capacitor have to be able to handle all of that voltage. If it was the same 1,800 microfarad capacitor with, let's say, 10 volts, it would be far smaller. It would be probably about this size. Okay, so for those of you online, we were talking about a physical capacitor that is present here in the classroom. To give you an idea, let's say if this was, let's say, 1 centimeter, then the capacitor we have here is about this big, maybe slightly thinner than that. All right, this was 1,800 microfarads and 350 volts. A similar sized capacitor, but a smaller voltage would be about this much. So let's say this was a 1,000 microfarad capacitor, but it would handle only about 10 volts. 10 volts or 15 volts. Okay. Next up is physical construction of a capacitor. A physical construction of a capacitor is 2 parallel plates separated by an insulating material. The separation what is happening with this? The separation is noted by D. In the area is the cross-sectional area of the plates. Now, in simple terms, that C is epsilon, the Greek letter epsilon, A over D. And epsilon is the permittivity. And it is epsilon 0 times epsilon R. This is absolute, it is a constant, and this is the relative, which is the material property of the dielectric or the insulating material. Okay, epsilon 0 times epsilon R. Okay, so conceptual question. Says the cross-sectional area of the plates. Now, if you have 2 plates, that are overlapping like this, you have two plates that overlap like this, which area should we take? The smaller plate or the larger plate? The average of the two. One answer is average of the two. Any other answers? It's the smaller. So when I said conceptual, here's the concept I want everyone to think about. The two palms of my hand together, I have a capacitor, right? If I take one away, is there a capacitance? No. So I need to have a second plate to have a capacitance. So now look at the figure again. Where are, or which area has two plates present and which has only one? Absolutely. The answer is plates that are overlapping. So guesses were good, right? Average, smaller, the guesses were good. But the concept again for a capacitor is we need two parallel plates separated by an insulating. If there's only one, then we don't have a capacitance. So if you have overlapping plates, then it has to have, the capacitance is present only in the overlap. So the epsilon A over D equation, the A is assuming that both plates are exactly the same size, whether they are rectangles, whether they are square, they are rolled up, and they are separated by an insulating material, exactly in the same place. Okay, that's what the assumption is. And again, in a quiz or an exam, I would provide all the values. It would be your job to determine what the capacitance would be. Okay, so let's see. Cover this, cover that. Capacitance equation is again exactly the opposite for the inductor. And so we had I, for an inductor, we had V. VL was L times DI over DT. Capacitor, we write the capacitor current equation IC is capacitance C times dV over dt. If you wish to find the capacitor voltage, you would integrate both sides. So you would have integral of IC, integral C dV over dt, and hence you would get VC as integral of IC. And I will talk about the integral limits when we actually get to the example problem. Okay. Power equation is still standard. P equals VI. And so we simply plug in the values for the voltage and the current in there. We get CV dV over dt. And the energy is the rate at which work is done. Comes out to be half CV square. And as a reminder, for an inductor, it was half Li square, the input current. For a capacitor is half CV square. All right, let's take a pause. Let me know if you have any questions thus far. Sorry, what? Energy. Yeah, W stands for the energy, rate at which work is done. Okay, so similar to resistors, if we have multiple inductors and multiple capacitors in the same circuit, we can reduce it down to one single equivalent inductor or equivalent capacitor. So if you have inductors in series, and doesn't matter how many inductors we have in series, between A and B, LEQ is the inductance measured between LAB, and we can write inductors in series are L1 plus L2 plus however many inductors we have in that series connection. They add up the exact same way that we would add up resistors. Inductors in parallel. Doesn't matter how many inductors we have, they add up exactly the same way as in resistors. So LEQ, again, measured between A and B, this is 1 over L1 plus 1 over L2 all the way to Ln. And then the reciprocal. Capacitors are the exact opposite. CEQ, total equivalent capacitance between the outer terminals, CAB, is 1 over C1 plus 1 over C2, 1 over Cn, and then the reciprocal. And then capacitors in parallel. CEQ measured between CAB is C1 plus C2 plus all the capacitors in parallel all the way to Cn. All right, let's take a pause. Let me know if you have any questions. Okay, any questions? Yes. There are derivations where we can show It's just that for non-E major class, we are time limited, so we don't show it in class. So the question being asked is how and why do these equations come about? And the answer is, I mean, there are equations we can show and derive the mathematical expressions and show. So if any student is interested, I can be happy to explain outside of class. Yeah. All right, so one thing before we go to the examples is that the last slide has a summary of all the equations that you would need, okay? So make sure you go through it. Again, it's just a summary of all the equations that we have looked at. And, you know, for the inductors and the capacitors, and they are duals of each other. They are very similar components, but the equations are exactly the opposite, exactly the same form, but opposite in many ways. And this will be important to keep in mind when we get to AC analysis. Okay. So having said that, let's look at these examples. I have 4 examples here. And these 4 examples, everything uses a capacitor, but the examples would apply equally to both capacitors as well as inductors. So for example, we have voltage for a capacitor given, and we'll be asked to find capacitor current. The same example as applied to inductor would be inductor current was given. Sorry. IL is given, and we're asked to find VL. And the other side would be that a capacitor current is given, and we are asked to find capacitor voltage. Same example for an inductor would be VC is given, and we are asked, VL is given, and we are asked to find IL. Okay. So we have 2 components, inductors and capacitors. So we have 4 quantities: inductor current, inductor voltage, capacitor current, capacitor voltage. If you're given capacitor voltage, you can find the capacitor current. A similar process would apply if you're given the inductor current and you're asked to find the inductor voltage. And then the other examples are where a capacitor current is given and you're asked to find the capacitor voltage. The same example would apply for an inductor in the form of inductor voltage being given to you and you're asked to find the inductor current. So again, all solved examples, the methods apply equally to capacitors and inductors. In this case, we are not doing any qualitative analysis. There is nothing to understand. We simply have the equations and we don't know what the circuit is, or we don't know what the circuit does. We are simply taking the equations and we are applying the values and performing mathematical calculations. So in this particular instance, it is as if we are not even doing any circuit analysis. Okay, we are simply doing a mathematical calculation. So in example 1, we are given a capacitor of 5 microfarads. We are asked to find the current. The voltage is given by this mathematical equation. Okay, so example 1. In example 1, we are given capacitor value of 5 microfarads. And we are given the voltage that is applied to this capacitor. Ten cos 6,000 T volts. Now, we don't know anything about this. We don't really care what the circuit is or circuit does. But we do know that a capacitor current I is given by the product of the capacitance and the time rate of change of voltage, C dV over dt. So we plug in the values. C is 5 microfarads, so 5 into 10 raised to minus 6. and then the time derivative of the voltage, which is 10 cos of 6000t. We simply solve this. Derivative of a cos is minus sine. So we have a minus at the front. And then we solve derivative cos of AT. So A comes outside 6000. And then, of course, derivative would be 10 sine 6000t. Or the final quantity of the derivative would be 10 sine 6000t. And so capacitor current would have a value of minus 0.3 sine of 6000t. So it'd be 5 into 10, so 50, 50 times 6, 5, 6 are 30, so 30,000, 3 into 10 raised to 5 into 10 raised to minus 6, so you get 0.3. Yep, right. And 6000t, and the units for the entire expression is still amps, obviously, because it is current. Okay. All right. Does the method make sense? Even though we don't have the circuit, we are again not analyzing the circuit at all. We're just taking a capacitor component anywhere in a large circuit. We are given the voltage. Sorry, we are given the current. No, we are given the voltage and you're asked to find the current. The same example with the same methodology for an inductor would perhaps look like this. So for an inductor, we can write that IL of t is given. So I of t is given as perhaps 10 cos of 6000t. And we are asked to find the voltage. And if you do the exact same thing, inductor voltage is L times di over dt. You'll plug in the values for L, you will plug in the value for I and find the time derivative and determine the product. Does that make sense? Any questions? Okay, then let's take a break. And it's 11:05. Let's meet back at 11:10. 5-minute break. In the meantime, I'm here. If you have any questions, feel free to ask.